Morning, Mr. Kane.
Morning, Mrs. G. It really is a new morning, isn't it?
Yes, this time we are really saying good morning.
You're not wearing the green sweater.
Nope, this is actually a new morning.
All right. So we're going to talk about polarity today, right?
Okay. Polarity of molecules.
And we talked about polarity of bonds, right?
Correct. Bonds can be polar if it's a polar covalent.
And that's like 0.4 to 1.9. That's polar covalent, right?
Yeah.
Okay. Anything below 0.4 is nonpolar. Anything above it is ionic.
Yeah.
But you're not talking about the polarity of a bond here. This says polarity of
Molecules.
So we can have more than one kind of polarity.
Correct, because you can have a polar bond and a polar molecule. You can have a polar bond and a nonpolar molecule, but you can never have a nonpolar bond and a polar molecule.
Okay. So my bonds, if my bonds are polar, I might have a polar molecule, or I might not.
Correct.
If my bonds are nonpolar, I definitely have a nonpolar molecule.
Yeah.
Okay. All right. But the polarity of the molecule is going to depend on how these bonds are arranged.
Correct.
And I can draw vectors.
So polarity is most dependent on the bonds and where the bonds are.
Right. So I can draw vectors on these bonds, and if I do it on the Vesper shape, I can see if they combine and add up, or if they combine and turn into no vectors.
Right. If they are opposite but equal, they'll cancel out.
If the vectors are opposite but equal, they cancel, and it's nonpolar.
Yep.
Right. If they don't cancel,
it's a polar bond.
It's a polar bond.
I beg your pardon. It's a polar molecule.
Oh, okay. I'm sorry. It's a polar molecule. So there's polar bonds, there's polar molecules, and there's polar bears.
Well, we know the polar bear is the easy part. It's
right.
the polar bonds and the polar molecules that are going to cause some difficulties.
Okay. All right. So let's talk about a molecule that's nonpolar covalent right away.
Which is very easy because the bond is nonpolar.
Right. This is a nonpolar bond. So I don't draw any vectors, and I know that it's a nonpolar covalent molecule because the only bonds in it are nonpolar ones.
Right. Nonpolar bond, nonpolar molecule.
Okay. So the electrons get shared equally. A lot of examples of these are diatomics. Something like CH4 methane gas. The carbon-hydrogen bonds are 2.1 minus 2.5, which is 0.4, which is nonpolar.
So carbon to hydrogen, any carbon to hydrogen bond will be nonpolar.
Those are automatically nonpolar.
So since the bond is nonpolar, the molecule is nonpolar also.
So polar covalent molecules.
All right.
The vectors do not cancel each other out.
Correct.
Right. So, for example, things like water, hydrofluoric acid, silicon,
silicon trifluoride.
With chlorine attached.
Oh, silicon trifluoride chloride. No, let's see, what would that be called? Silicon chlorotrifluoride?
Probably.
Something like that.
Yeah. And then there's, but not silicon tetrafluoride.
Nope, I'll bet that's a tetrahedral shape.
All right. So here's the deal. If we've got water, notice I've got the sigmas written in already, but maybe we should draw vectors instead, because we talked about vectors. So if we draw in vectors, you can see that the two vectors don't point directly at each other.
Correct.
If they point directly at each other, they would cancel each other.
Technically speaking, the polarity of the bond has magnitude and direction, correct? I mean, we've already calculated magnitude. That's the difference in electronegativity, per se, kind of, right? And the oxygen is more electronegative than the hydrogen, so the electrons are going towards the oxygen, making it more negative.
Right.
Positive end towards the hydrogen, arrowhead towards the oxygen. Those are vectors, direction and magnitude. And truthfully, we're not too much interested in the magnitude so much as the direction.
As long as it has some direction.
Yeah.
An arrow going up or left and an arrow going up or right. We wind up, if we would combine those together, with an arrow that goes straight up.
Right, and there's nothing across from it to cancel it out.
So since this is my combined vector and it exists, it isn't zero, we've got a polar covalent bond.
Yeah, and I call it a resultant vector, but same thing.
Resultance is right.
Yeah. It's the sum of the two, and there's nothing to cancel. Real world importance.
Okay. Water is polar. We just saw that, right?
Correct.
Water is a polar molecule.
Yep.
So what that means is it can dissolve other polar molecules.
Like dissolves like.
Yeah, that's a rule. We're gonna use that rule later when we do solutions.
Correct.
Soap is mostly nonpolar, though.
It's a bunch of hydrocarbons.
Yeah, that's to say that it's long chains of carbon bonds.
Right. which are nonpolar.
Okay, it turns out that on soap, at the very, very end, you get a negative carboxylate group. So what happens is this, it's attracted to the polar water molecules, just the very end of the soap molecule. And these carbon chains wind up sweeping away the nonpolar dirt molecules, because nonpolar sticks to nonpolar, so soap sticks to dirt. And the very end of the soap sticks to water. So you get clean by using soap, which can take care of both.
Oh, jeez. All right.